In this section, we're going to look at 4 more tests for deciding whether a series is convergent or divergent. The first one that we are going to look at is the ratio test. The ratio test involves a lot of tedious algebra. So your algebra skills really need to be on point here, or you may not like this test. So if we've got a series, a sub n, what the ratio test is going to do for us is it's going to check to see if, as we move along in the sequence of values that we're adding together, we need to make sure, we know from the divergence test that the sequence has to go to 0 if we have any hope of this thing converging. But also we mentioned that it's got to go to 0 pretty quickly. So what the ratio test is going to check is to make sure that these terms decrease by an order of magnitude every single time. So the way that we're going to check that is we are going to compare just a general form of one term with what the next one would be. So if the limit as n approaches infinity of a sub n plus 1 over a sub n is, if you calculate this limit and the value comes out to be less than 1, that means our series is convergent. Now the reason that less than 1 means convergent is because we've got the next term in the sequence on the top. So if the previous term is larger and the next term is smaller by an order of magnitude, then the value of this fraction will always be less than 1. We're not going to know specific numeric values to plug in here. We're going to do this algebraically with our index n and have to use a lot of properties of algebra to simplify this. If the limit for that fraction comes out bigger than 1, that means that the values are not decreasing by an order of magnitude. The values are in fact getting larger. A fraction will come out greater than 1 if the top is larger than the bottom. Well, if the terms in our sequence are getting bigger, then there's no way that this sum is ever going to stop, because we're just continuing to add larger and larger and larger numbers along the way. If the value of that limit is equal to 1, then the test is inconclusive. It still could be that a sub n plus 1 is smaller every time, but it's not an entire order of magnitude smaller. It's just smaller by some sort of ratio, some sort of coefficient usually. And this usually means that, like we have a polynomial and they have the same power. It's possible that that is convergent or divergent, but this test really can't tell us either way. And the fact that the limit equals 1, meaning the test is inconclusive, that doesn't mean that that's our answer. Our answer is not the ratio test is inconclusive. If we perform one of our series tests and it's inconclusive, that means we need to try a different test. So let's take a look at a couple of series that we can determine convergence or divergence using the ratio test. Now the algebra on these takes a few minutes. These aren't really quick tests like the geometric series test or the p-series test. These ones are quite a bit more involved mathematically. So we want to determine if each series is convergent or divergent. And the first one we're going to try is the sum from 1 to infinity of 2n minus 1 over n factorial. So because of that factorial, this is not a geometric series, it's not a p-series, it's not something we know how to integrate. So a lot of times when you see a combination of several different types of expressions being combined, usually with multiplication or division, the ratio test is probably going to be the way to go. So what they gave us is the a sub n. All of this stuff is a sub n. And we need to write out what the a sub n plus 1 expression is. So remember, n is just like a variable. And I want to know what this is going to look like if I replace n with n plus 1. So instead of 2 times n, we'll have 2 times n plus 1, and then minus 1, all over n plus 1 factorial. So that's what a sub n plus 1 is going to look like. Now we need to stack them and calculate the limit. So on the top we put the a sub n plus 1, and the bottom we put the a sub n. So this is going to start off as a really messy fraction because we're going to have a fraction divided by another fraction. And I'm going to go ahead and simplify this before I write it out here. A sub n plus 1 is 2n, and then we have plus 2 minus 1, which is really just plus 1, all over n plus 1 factorial. And then on the bottom we have our a sub n, which is 2n minus 1 over n factorial. Instead of trying to perform fraction divide by fraction, we will flip and multiply. And when we do that, we will have some things that can cancel out. Now, those two n's do not cancel because of the addition or subtraction. We either have to cancel that entire term or leave it alone. But n factorial, n plus 1 factorial, those can be simplified. Because if you remember what factorial means, n factorial means we're going to do some repeated multiplication. We're going to start with the value that we're given, and we're going to work our way down until we get to 1. N plus 1 factorial, if we follow the same factorial rules, it's a repeated multiplication. You start with the number that you were given, and you work your way down. You subtract 1 every time. So if I subtract 1 from that, my next term is going to be n, and then n minus 1, and then n minus 2, dot, 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 all the way down. So at some point, factorials always are going to match, and a whole bunch of their terms are going to simplify. So if you compare what these two have in common, everything after the n is going to cancel. So really, the only thing we have left after that simplifying is where we had n plus 1 factorial, there's going to be an n plus 1. So now I'm going to multiply my fractions. The only thing left in the numerator is 2n plus 1. In the bottom, I have n plus 1 times 2n minus 1, which is 2n squared plus 2n minus n will result in just a plus n, and then minus 1. And we want the limit as n approaches infinity, so what we can do is we could compare the degree of our numerator with the degree of our denominator. Since the degree of the denominator is larger, this limit is 0. Now the rules for the ratio test said if you calculate this limit and you get any answer less than 1, which we have, that means our series is convergent. So let's take a look at another one. This time we've got a series from 1 to infinity of 2 to the n over n squared. Now those look very similar, but they're actually very, very different. In our numerator we have an exponential function. On the bottom we have a power function, or just like a piece of a polynomial. So what we are given in the series is the a sub n. And we need to write out what a sub n plus 1 will look like. So all we have to do is go into a sub n and replace the n's with n plus 1's. So we'll have 2 to the n plus 1 over n plus 1 squared. And then the ratio test tells us to set up the fraction a sub n plus 1 over a sub n. We'll do as much algebra simplifying as we possibly can, and then we'll take the limit. So remember, this is going to start off really messy because we've got a fraction divided by a fraction. In the top we have our a sub n plus 1 term. In the bottom we have our a sub n term. And instead of dividing, we flip and multiply. And we should have some simplifying that we could do. Otherwise, this limit would be very difficult to calculate. Now, the n plus 1 squared and the n squared do not have anything in common to cancel. When you are working with polynomials, the factors have to match perfectly in order to cancel, and they don't. In our numerator, n squared technically means n times n. And here in the denominator, n plus 1 squared means n plus 1 times n plus 1. So n and n plus 1 are two completely different factors, so there's not really anything we're going to be able to do with those. But our exponential piece, the 2 to the n plus 1 and the 2 to the n, since they have the same base, when we have two numbers being divided that have the same base, we can subtract the exponents. So n plus 1 minus n would just leave us with 1. So really that simplifies down to just a 2. You just have 1 2 remaining in the top. Another way that I like to see this is this exponent tells me how many of them I have. So in the top I have n plus 1, in the bottom I have 2. And we can only cancel out the smaller number. So I can cancel out n of them from each position, and I'll be left with 1 additional in my numerator. And then we also have the n squared, and then we have n plus 1 squared. Now this might be easier to calculate the limit if we FOIL out our n plus 1 squared. So we've got 2n squared over, well this means n plus 1 times n plus 1. So n squared plus 2n plus 1. And at this point we can use the rule about the exponents. In this case, the exponents match, and when that happens, you use the leading coefficients to decide your answer. And usually, if there's nothing there, we just understand it to be a 1. So our solution here is 2 divided by 1, which is just 2. So we've done all of our algebra simplification, we've calculated our limit. Now we can go back to see what the ratio test tells us, and it says if you calculate that limit and you get an answer that's bigger than 1, that means our series is divergent. I want to show you one more really quick, just so you can see the inconclusive case and what exactly it's going to look like. So for this last one, with the ratio test, we've got the sum from n equals 1 to infinity of 3n minus 5 over n plus 2. So what they give us is the a sub n. And then we need to write out what a sub n plus 1 is going to look like. So I'm going to go and I'm going to replace the n's with n plus 1's. And when I go to stack these in my limit, I'm going to simplify them a little bit. So we want a sub n plus 1 on top. That's really 3n plus 3 minus 5, which is 3n minus 2. And here we have n plus 1 plus 2, which is n plus 3. In the denominator, we put the original a sub n, which is 3n minus 5 over n plus 2. And we're pretty much going to do this every single time. Instead of fraction divided by fraction, we will flip and multiply. And there are no matching factors here. You cannot cancel when you've got a plus or minus holding things together. We can only cancel if it's multiplication that's holding the entire thing together. So because all of these have pluses and minuses, we can only cancel if the pieces match perfectly, and none of them do. So that means we're going to have to keep all of it. And to recognize the limit, it would probably be easier if we multiplied this out. So in the top, we'd have 3n squared plus 6n and minus 2n, so that's plus 4n, and then minus 4. In the bottom, we have 3n squared plus 9n minus 5n. That's going to be a plus 4n, and then minus 15. So we can do the rule where we look at our degree for our numerator and a denominator. They match. That means we are going to use these leading coefficients to decide our limit. So our leading coefficients are 3 and 3. 3 divided by 3 is equal to 1. That means that the ratio test is inconclusive. It doesn't tell us that it converges or that it diverges. It just means the ratio test cannot be used to solve this problem. We would have to use a different test. We are going to slide the root test into this video as well, because the root test is really easy. And then I'm going to do a separate video for comparison tests, because they could be a little bit more difficult. So for the root test, we've got a sum of a sub n's. It's an infinite series. And if we take the limit as n approaches infinity of the nth root of a sub n, we can tell just by the result of that limit what our answer is going to be, whether it's convergent or divergent. So the rules for the root test are exactly the same as for the ratio test. If this value comes out to be less than 1, then our series is convergent. If it comes out to be greater than 1, then our series is divergent. If it comes out to be equal to 1, then the test is inconclusive. That means we cannot use the root test on this particular series. We need to rework it with a different test. So there are only certain types of series that I suggest you use the root test for. Since we're going to have to be doing this root n or nth root calculation, you really should only use the root test when your series has an nth power in it. So we've got something to the nth power. Then calculating that nth root will be really easy because the nth root and the nth power will cancel. If your series does not have an nth power on it, simplifying that nth root would be very, very difficult. So we only use this if our series as a whole is raised to the nth power. So two quick examples. Just like the rest, we're going to determine whether each series is convergent or divergent. And for the first one, we're trying to calculate the sum from 1 to infinity of 2n minus 5 over 3n to the nth power. So the other type of series that we saw that had an nth power was the geometric series. So the rules here are similar to a geometric series, where if the base is less than 1, well, our base is going to have some variables in it. That's one big difference between these series and the geometric series, is with these we can have variables inside of our base. With a geometric series, we only had a single number as the base of that exponential expression. So that's where the limit comes in. The limit helps us to simplify down all those variables in the base. But it's the same. It's the same rules. If your base is less than 1, it's going to be convergent. If it's greater than 1, it's divergent. With geometric series, if it was equal to 1, it was also divergent. But because these series are slightly different and we have variables in the base, the equals one is inconclusive and we've got to try something different. So what they give us is the a sub n, and with the root test, what we're asked to calculate is the limit as n approaches infinity of the nth root of a sub n. So here you'll see exactly why I suggest you only use this test if your series has an nth power on it, because this nth root and nth power will cancel each other out. And we'll be left with a pretty easy limit to calculate. So we've got the limit as n approaches infinity now of 2n minus 5 over 3n. Those two expressions have the same degree, so we're going to use the coefficients and see that the limit is equal to 2/3. And since that answer is less than 1, that means this series is convergent. For the next one, we have the sum from 1 to infinity of 1 plus 2 over n to the nth power. And again, because my sequence of numbers is all raised to the nth power, the nth root test will be a good candidate for trying to figure this out. So everything they gave me there is the a sub n that we're going to put inside of the nth root. What we need to calculate is the limit as n approaches infinity of the nth root of all this stuff. And because we're being very selective on what type of series we use this test on, we should always be able to cancel out the nth root and the nth power. And we're just left with the limit as n approaches infinity of 1 plus 2 over n. We could take the limit of those two pieces individually. The limit as n approaches infinity for 1 plus the limit as n approaches infinity for 2 over n. We also could get common denominators and combine them into a single fraction, and that would work as well. But the limit as n approaches infinity for 1 is just 1. There's no n's in there to ever change our value. The value for this expression is always going to be 1, no matter what the n value is. And then on that second term, if you compare the degree of the numerator, the degree of the denominator, the degree of our denominator is larger. That means that limit is 0. So we get 1 in this case. And unfortunately, when we get an answer back of 1 on the limit for the root test, that means the root test is inconclusive, and we would have to figure out a different way to work this problem.